Hey guys, this is Algebra 2, Chapter 6, Section 7. It's going to be our last section of this chapter, and it's going to deal with inverse relations and functions. So, remember that a relation is just a correspondence between an x coordinate and a range and a y coordinate, or the domain and the range. And for something to be a inverse relation, so if we have a relation, some relation where we have some a corresponding to some b, if we were to have the inverse to that, we would just essentially switch the A and the B. Okay, we would essentially switch the A and the B, and that's an inverse relation. For something to be a function, if you remember, every x corresponds to exactly one y, but we can't have an x correspond to more than one y. So if the relations form a function and the inverse forms a function, then we have something called inverse function as well. And we have something called an inverse function where we have a set of relations such that they are opposites of each other. And we can do certain things with inverse relations. So in this example here, we have this relation, and they graphed it. Yeah. We have this y of x, and the reason why we have this y of x, so if we have a function y equals x, right, the inverse of that would be everything that's a y is switched with the x, and everything that's an x switches with the y. So we would have x equals y. They switched places. All right. And if you notice, x equal y and y equals x are essentially the same. It's the same line. It's the same function. It's almost sort of like a base function. It's sort of like in the middle. And y equals x is just a straight line with a slope of 1 that goes right down through the origin. Straight line, positive line with a slope of 1 that goes through the origin, y equals x. And this is sort of the base inverse function where both of the guys are the same thing. And since they're both the same thing, every inverse function that you can get out of that always has an equal distance from that particular function. So here, if we look at this part here, the first dot down here is 0 and negative 1. So when we do the inverse, it's going to be negative 1, 0. They switch places. All right. So 0, negative 1, negative 1, 0. And look, they're the same distance from y equals x. These two guys, the same distance from y equals x. Same distance from y equals x, same distance from y equals x. So when you have a set of inverse relations or inverse pairs or inverse functions, those guys are always going to be the same distance from y equals x. And then you get your inverse. Is it a function? Yes, because it passed the function rule where you, or the vertical line test. So we can say that this is a function. If we look at this guy, I'm not going to graph it, but if we do the whole domain and range thing. We have in the x part 0, 1, 2, 3, -5, -4, -3, -3. So that's function. Definitely. This is a function, and the reason why it's a function is because every element of x has one y. This x has this y, this x has this y, this x has this y, this x has this y. Every function of x has exactly one y. Or you can even draw it like this. That's how I should have drawn it, actually. This is how I should have drawn it. This is okay. You can have 2x have the same y. That's okay. The other way around, though, it's a problem. So if we do the inverse, and we do the domain and range, we switch them. So you have -5, -4, -3, and 0, 1, 2, 3. Again, that moves. That wait, yeah. And then we have this guy. Now we have 1x with 2 y's, as opposed to 2 x's with 1 y. So in this case, we don't have a function. It wouldn't pass the function rule. And if we were to graph this, we would see basically like a vertical line. It would be like -3, right? And this would be -3 and 2, -3 and 3. And that wouldn't pass the function rule. That wouldn't pass the vertical line test. So this is not a function. Okay. When we're trying to solve for an inverse relation and stuff, all we do is we switch the y's and the x's and then solve for x. So this is the initial function. This is the first function. If I wanted to find the inverse, the thing that I would do is the y's and the switches x and the y's are going to switch. We're going to switch the x and the y's. So now we are going to have x equal to y plus 8. And now we're going to solve for y. Subtract 8 from both sides. X minus 8 equals 2y, and then divide both sides by 2. And I get 1/2 x minus 4 equals y. Or you can write it as y equals 1/2 x minus 4. This is a function. This is also a function. So that is an inverse function. All right. This is the inverse function for that guy. Y equals 1/2 x minus 2. All right. And this would fit along the equation y equals x when you were to graph these guys. Alright, so if we were to graph this, so the two graphs are y equals x and y equals 1/2 x minus 4. if we were to graph these guys, so our first line is going to be y equals x. This is our baseline. This guy is where the inverses of each guys are the same. And the first guy was y equals 2x plus 8. There, that would look like that guy. And then the inverse. So if we look here, this is 0, -4. So if we were to switch it, it would be -4, 0. And that guy would be the equidistant from this guy. So it's going to be some line that looks like that goes through here and cuts off. That was y equals 1/2 x minus 4. Again, notice how it comes off, breaking off from y equals x, and these guys are equidistant from each other. Boom, boom. It's like a mirror from y equals x. When we do inverses in function notation, so f of x equals some equation, we'll go with the 2x plus 8. When we want to write this in function notation, we can say f of -1x. That means inverse. 1/2 x minus 4. Alright, so f to the -1, that means inverse function. Okay. Things to note about inverse functions. I actually like this example here, so I'm going to go through it. So we have a function f of x equals square root of x minus 2. Okay. When we think about the domain of this particular guy, the domain is going to be all real numbers such that they're greater than 2. Because if I put greater than or equal to 2, if I put 3 less than or equal to 2, because x can't be negative. So x has to be greater than or equal to 2, because if I put like 1, then I get -1, and I can't do the square root of a negative number without using imaginary. So here we're just using positive roots. So x, in terms of the domain, has to be greater than or equal to 2. So when we think about the range has to be, since I can't have any negative numbers after I square root this, the range has to be greater than or equal to 0. Oh my god. Greater than or equal to 0. Okay. So if I were to find the inverse, alright, so instead of saying this is f of x, I could say this is y, and I'm going to switch them to find the inverse. So the inverse would be x equals the square root of y minus 2, and I'm going to solve for y. First thing I'm going to do is I'm going to square both sides, so I can get rid of the square root. That gives me that x squared is equal to y minus 2. Then I'm going to add 2 to both sides, and I get that y equals x squared plus 2. Y equals x squared plus 2. But here's the conditions. Then to write this in inverse form, it's going to be f of negative 1 x equals x squared plus 2. When you do inverse functions, the domain of the original function is now the range, and the range of your original function is now the domain. So when I do this, the domain for the inverse is going to be y is greater than or equal to 0, and the range is going to be x is greater than or equal to 2. Okay? Which kind of makes sense because for I can't, they have to be the same, right? We're switching the x and the y's. So if we're switching the x and the y's in our relation, then the domain and the range must also switch. That makes actual sense. Is it a function? The inverse? It's a function when f is greater than 0 and equal to 0. And since that is within the range, we can say that this is an inverse function. And then you think about it, it's just an x squared raised vertically by 2. So yes, it is a function. Here they give us a g of x plus f of x, or g of x, equals 6 minus 4x. So the domain is all real numbers, and the range is all real numbers. So if we're talking about the inverse, inverse would be if we were to switch to x and the y, so this is x equals 6 minus 4y. Add the 4 to both sides, 4y to both sides. Subtract the 6x, subtract the x, so it'll be negative x minus 6 plus 6 divided by 4. Y equals negative 1/4 x plus 3/2. And we can say that that's going to be g negative 1 of x is equal to negative 1/4 x plus 3/2. Alright, so that's our inverse. Okay. So if I was to switch the domain and range, those guys would be exactly the same. So the domain of f of 1 is all real numbers. The range of f of 1 is all real numbers. Okay. Is it a function? Yep, I would say it's a function. For every element of x, there's an element of y. This is a linear function. This is a linear function. So yes, this is a function. Alright, here they just want us to find out what the velocity is given a certain distance. So in order to do that, we just have to do the inverse. So d equals v squared plus over 19.6. So what I'm going to do is I'm going to multiply both sides by 19.6. And that's going to equal v squared. Then I'm going to square root both sides. So my inverse is going to be that v is equal to the square root of 19.6 times d. And in this case, d equals 24. So how fast is this person going? So 24 times 19.6 square root. This guy is falling at a velocity of 21.69 approximately meters per second. No, not seconds squared, meters per second. One-to-one function. This says that if something is one-to-one, it is true value of y corresponds in range exactly to one x value of domain. One-to-one function has an inverse that maps onto a to b, and then f of -1 must map on the b to a. Sorry, so what a one-to-one function is that if it's a true one-to-one, if I have some f of a equals b, then the inverse f of -1 of b has to equal a. They have to. And if they do, and they're both a function, then we call that a one-to-one function. If this is a function, and if this is a function, then they're one-to-one. Right? And when we know that they're a one-to-one function, that we can do something with its composite. And what the composite says is that if I take the composite of the inverse first, and then do the composite of the actual inverse function of x, then my answer is going to be x. It's going to be the same thing. Or, it says and, but it's or. If I do the function first of x, then the inverse function, or actually if I do the inverse function first of x and then the function, then I also get x. Alright, this is basically the y equals x of each other. It's an identity. If I have a composite of the inverse and I put in some number, that same number should be my answer. Or if I flip it and if I have the inverse and then the composite of the inverse and I put in some number, I should get the number. And one of those is going to be a function and one of those is not. So the example that they give here is that we have a function. And the function is f of x is y over x minus 1. And then the inverse of that, you get eventually 1 over x is plus 1. To see if this is an inverse function, that it follows the inverse function rule, if I was to plug in 1 into the inverse function, this would be 1 over 1 plus 1. And that gives me 2. Then I'm going to plug in the 2 into the original function, and I get 1. So I plug in 1, and I get 1. So this is a one-to-one. This works. If I do it the other way around, and I do the f of x first of 1, so I plug in 1 here, I get 1 minus 1 is 0, I get 1 over 0, and that's not work because you can't divide by 0. So it doesn't exist here for 1, however it is 1 over here. And that usually happens with these types of problems. So here they give me that g of x is equal to 4 over x plus 2. So if I wanted to do the inverse, I switch the x into y. X equals 4 over y plus 2. Multiply both sides by the denominator. So here, this would be y plus 2. What I do on one side, I do to the other. That goes, that goes. So I have y plus 2, x equals 4. Then I divide both sides by x, and I get y plus 2 equals 4 over x, and then subtract 2. So y equals 4 over x minus 2. So then I can say g of negative x is equal to 4 over x minus 2. Okay, 4 over x minus 2. So that's g of x. They want to know what is g of prime, or g of negative 1 x. So g composite g of negative 1 of x, or of 0. So the one closest to the 0 is the one I do first. So I'm going to do first g of negative, the inverse of 0, which is going to be 4 over 0 minus 2. And I can't do it. Doesn't exist. I can't divide by 0. So, it doesn't exist. Null set. So that's not my one-to-one function. Now if I do it over here and do g of negative 1 composite of g of 0, in this case I'm going to do this first, and it's going to be 4 of 0 plus 2, which is 4 over 2, which is 1/2. Then I'm going to plug this 1/2 and put it down here into g of negative 1. So then the next step is going to be 4 of 1/2 minus 2. 1/2, 4 divided by 1/2 is 8. So it's going to be 8 minus 2, and 8 minus 2 is 6. No, that can't be right because we need to have a 0. What am I doing wrong? No, because this is 2, because I can't do mathematics. Alright, so this is 4 divided by 2 over 2, which is 2 minus 2, which is 0. There you go. Alright, so then this works. So this guy is the one-to-one composite function of g of x and g prime, g of the inverse of g of x. Okay. Alright, that's this section. Hope you have a great rest of your day.